Alright, class. I wanted to cover the last part of class that we missed and start talking about uh, at least introducing the origins of bioelectric phenomena, which will be helpful in understanding ECG, EEG, and EMGs. Okay, so let's get this PowerPoint started. I apologize if this is posted late. That's partly because I did record this yesterday, but I unfortunately didn't include audio in that recording. So I'm doing this again for the second time, but hopefully it's more improved than the first time. Alright, so we last left off talking about the potentiostat, and just to remind you that these are kind of a class of circuits that you can use to basically interface with three electrochemical cells. So if you recall, in that scenario, you have three electrodes. One's a reference, one's a counter, and one's a working electrode. And we went over some ways to actually limit the amount of current that gets sunk into the reference and how to control the voltage between the reference and the working electrodes. So I encourage you guys to review that and make sure you understand how to solve those kind of problems. We did some board work, I believe, and I think these are on your homework on the problem set, so take a look at them. Prove to yourself that you can derive what V out is given these various resistors here. So that's just going to involve you doing some node voltage analysis in this here. And then also convince yourself of what V cell is in this case, and in this case as well. So definitely do that. Okay, so let's get now to Coulter counting. This is kind of the home stretch of the biomedical sensors portion of this class. So Coulter counters, as we're going to see in the next slide, is a method to measure the size of cells, but also to measure how many cells are passing a given point. Some applications of this are obviously if you're trying to do some measurement of, let's say, someone's immune system, and you wanted to count the number of white blood cells that are present in the person's blood. You would need some form of counting those white blood cells. In the past, this was done by putting a sample of blood under a petri dish and using a microscope and manually counting. And obviously, that's not as accurate because you can have a wide range of counts for a given person counting the cells. On that note, I did post a reading on Coulter counting, the history, so I definitely take a look at that and read it. It's fair game for on the test. Any general information from that will be used. Okay, so what is Coulter counting? So before I get into the exact apparatus, I want to just give you some quick basics, and I'm gonna draw an analogy to just using a regular conductor because it actually will explain quite a bit of how a Coulter counter actually works. So in a Coulter counter, if you look on the right here, you're going to have a cylinder that's filled with an electrolyte. So that's going to have some ions in here. So you have some ionic conduction or ionic currents that can go through this cylinder here. The analogy to that, I guess, from an electrical standpoint is you have just a conductor. So a conductor, instead of ions moving around or that can freely move around, you have electrons that can freely move around. And so we're going to draw that analogy here. We know from basic physics that we can calculate the resistance of this conductor by basically taking the resistivity of it, which is a material property, multiplying it by the length of this thing, and then dividing by the cross-sectional area of this cylinder, and that's going to give us resistance. So back to the electrolyte analogy, you can actually use a similar equation here where the impedance, I'm going to call it impedance, and you'll see in a second why, because there's some equations that we're going to get to that use R. So the impedance of this electrolyte cylinder, think of it like a little chamber with electrolyte inside of it, is also going to be rho L over A, where L is the length, A is the cross-sectional area, and rho is the resistivity. The biggest difference is that the resistivity of an electrolyte is a strong function of the ions that are in here and the concentrations of those ions. And we're not going to get to that in this class, but if you're interested, we can talk about it on an individual basis. But you'll typically be given rho for an electrolyte solution. But it's definitely an extra calculation if you are not given rho and you have to figure out how the ions are affecting rho. Okay, so back to the analogy. In the analogy of the electrical conductor, let's say that you put a nick inside the conductor. So you cut a piece of this kind of wire off. Within this section here, you're gonna have a reduced area, and so if you kind of take it piece by piece, you can find that because you have a decrease in area in a small portion of the conductor, that's going to effectively increase the resistance across this conductor here. And so another way to think about this is that because you have a nick, if you assume this is air sitting out here, that the resistivity of air is quite large compared to the conductor. So no electrons are going to, or less electrons will freely move through this conductor than if you didn't have the nick. So on a similar kind of note, if you take an electrolyte and let's say you don't nick the actual container, but instead you place a particle, in this case it's a triangle, because we're lazy in the drawing here. It could have been a sphere. But let's say that you do have a triangle, and this triangle represents a particle that's sitting inside the electrolyte. And we're going to assume that this particle is not conductive to ionic currents. So, when an ion comes here, it's going to go around it. Well, this is taking up volume within the electrolyte. And because of that, it decreases the effective area and basically the volume that you have an electrolyte that is more conductive to ions. And so what this is basically saying is that the particle is basically obstructing the flow of ionic current through this electrolyte. And what that's kind of leading to is that if you can design some apparatus that has a quantified volume, and if you can pass particles through that electrolyte, particles that are not ionically conductive, then and if you were able to measure the resistance or the impedance change across this electrolyte channel, then you're able to also detect when there is and when there isn't a particle sitting inside this electrolyte. And we're going to find later as well that you can actually even get an idea of how big that particle is, right? So let's play kind of a little thought game here. If this triangle was much bigger, it would take up more volume and take up more area and even more length as well. So it would effectively change the impedance of this electrolyte even more because it's bigger. And so if this was bigger, then the resistance or the impedance would also get bigger. If this was much smaller, then the impedance would get smaller. Now the question becomes, well, what's the mathematical relationship between how big this is and how much impedance change you get? Because that's kind of what we're interested in. So we'll get to that in the next couple of slides and even in the written notes. Okay, so how does this actually work? So on the left here, you're going to have the tube, and you have the actual apparatus on the bottom here, shown down here. So the way this works is that you're usually going to have a glass tube where everything takes place. Within that glass tube, you're going to have an electrolyte, and within the electrolyte, you're going to have particles suspended in here. And those are usually the particles that you're interested in. So it could be cells, it could be any other particles that you're interested in measuring that are going to be counted. Then you're going to have these very small opening called an aperture, and you're going to have basically these two electrodes that are sitting inside and outside of kind of this inner tube here. It's like an inner kind of tube that's sitting in this bigger tube. And this opening is called an aperture. And you're going to induce the flow of ions between this aperture by basically providing an electric field between the electrodes. So this is like a glass, if you can imagine it, and it's insulating. So current's all going to go through this little hole here, or I should say ionic current, through this hole here and come back this way. So now, and there's more details in the paper that I've posted if you want to figure out how exactly it's pulled through this hole. But the message is that once you have a steady flow of electrolyte, you're also going to get some particles that are following that flow. And the opening, the aperture, is also going to be the area we call the sensing zone, because that's where we're going to actually be sensing when the particles flow through it. So when there's no particle flow through there, there's going to be a kind of a base impedance that you can measure between this small sensing zone here. When a particle passes by, if you think back to the previous slide, that's going to effectively increase the impedance, because now you have a particle which is going to be non-conductive to ions. And so that's going to create a change in impedance, which, because we have a constant current flow, will manifest itself in a change in voltage across those electrodes there. All right, so once that happens, you will measure that, and let's see what kind of plots you get when you have these particles passing. So as I mentioned before, a change in resistance in electrolyte will be measured as a voltage pulse. If you kind of go down here, you'll see that this would be the glass, the inner tubing. Here's the aperture area, and the area bounded by the aperture is going to be the area we talked about previously here. Okay, so if you can measure the impedance of this small area of electrolyte here, you're going to find that when there's no particles, you're going to have a base conductance, so G versus time. G being conductance, so it's just the inverse of resistance. You're going to have a certain conductance, so it's conductive. And then once you have a particle going in there, it's going to dip down in value, because now it's less conductive because you have an ionically insulating particle passing by. And there's a couple of things that I want you to take from this picture down here that are stated up here. So let's again play some scenarios in our heads about what can happen. So if this particle is bigger and goes through this small opening here, that's going to cause a bigger change in conductance in this case, right? So you're going to have a bigger drop off in conductance because you're taking up more area in here. So if you have a bigger particle, you're going to get a bigger dip. In terms of measuring voltage, that's going to result in a bigger voltage spike than if you were to have a smaller particle. The other thing too is you can also figure out how long does it take this particle to get through this small distance as ionic current flows through here. And that can be seen by this picture again, in that if you measure the time that you dipped in conductance to the time you go back to the original conductance, that amount of time is related to how fast this particle is moving through that space. So you can actually get a lot of information from just this one change in conductance in time. So what Coulter and his colleagues found is that, and this is what's called the Coulter principle, is that the amplitude of the voltage pulse produced by the entire apparatus is proportional to the volume of the particle that produced it. And again, that just goes back to bigger particle means bigger conductance or resistance change, which means bigger voltage change. And from the rate perspective, it also means that the voltage pulse number and the pulse rate are proportional to the particle concentration. So If you have more particles going in per unit time, that means you have a higher concentration of those particles, which mean that you can then sense that because you're going to get very um, consecutive spikes in voltages. Um, so that's the other thing that comes out of it. Um, Also, the pulse duration, like I mentioned before, is proportional to particle flow or speed. So three things there, right? First is amplitude of the voltage pulse is proportional to the volume of the particle. So you can distinguish from basically different size particles. And we'll see the equation for that later. That the voltage pulse number and the pulse rate are proportional to how many particles per unit volume there are in this solution, and the duration of the pulse is equal to or proportional to particle flow and speed. So you can get a couple of different parameters here by just using this simple apparatus. Okay, so let me go to the notes I have here and go way down. And just for sanity's sake, let me make sure that I am recording still, and I am recording audio. I am. Okay. All right. So here's an example I give, and what I'll say is, well, actually, let me go over the notes first, and then we'll jump to the example. So this is like what I mentioned before. Flow through electrolytes is similar to flow through conductors. So if you have an electrolyte channel, it has a cross-sectional area A, a length L, that you can find the impedance Z of that channel with no particles inside. And as I mentioned before, rho can be calculated by knowing the concentrations of the different ions that are sitting in here. Okay, so if we do have a cell in our chamber here, and just for this class to make it easy on us, we're going to assume that the cell is a sphere and it has a radius of lowercase r. Okay, obviously that's not true, that's an assumption, but it does make our life a little easier in terms of figuring out how exactly the impedance will change. So knowing the area of the channel, of the electrolyte channel, we're going to call this to be the radius, is capital R subchannel. It turns out that you can actually derive this, that the change in impedance is going to be basically approximately equal to 2 rho r cubed, r being the radius of the cell, over pi times the radius of the channel to the 4th power. Alright, so that's why I don't use capital R for resistance here. We're using impedance just to keep our symbols kind of from crossing over. So with that, you can figure out what the new impedance will be, and it's in units of ohms. And so what I wanted to do in this example is to give you an idea of the kind of impedance changes you're going to measure for one cell. And just to kind of give you an idea before we even start, this delta Z is proportional to the radius cubed. So even a small change in radius of the cell is going to yield a relatively steep change in the impedance change at the very least. So let me give you some ideas of the kind of diameters you'll see when we're talking about different cells. So platelets are just really small fragments of red blood cells that are used for like clotting. So when you cut yourself, your blood will basically use platelets to kind of clog up any openings in the blood vessel. Those are about 2 micrometers in diameter. Red blood cells are about 7 micrometers in diameter. So just again, we're assuming that these are spheres, but they're actually not spheres. Like a red blood cell is actually more like a disc. Basophil, they're actually definitely not spheres. They're very weirdly shaped. But if we assume that they're spheres, they're about 10 micrometers in diameter. So basophil is a white blood cell. So we're going to take a platelet and then take a basophil, and we're going to see the difference that basically a 5 times change in diameter can make on a delta Z. Alright, so let's assume in this case that we have a 100 micrometer long channel with a 30 micrometer opening, and we're using this as a Coulter counter setup. So what I'll first say is measure the impedance of the channel, assuming that rho is 0.5 ohm meters. All right, so to start this off, you know off the bat that the impedance is equal to rho times L over A. A is just because we're dealing with a cylinder in this case, because I didn't really tell you otherwise. Then it's just going to be pi r squared times the channel radius. And if you calculate that out, the base impedance is going to be 70.74 kilo ohms. And like I mentioned last time in class, here I did round off quite a bit. We're talking about kilo ohms here, so don't round off too much, just to be safe with these kind of calculations. All right, so if I wanted to see what for that channel, like how much of the 70.74 kilo ohms of that impedance will change when I put in a platelet into that channel. So the radius of the platelet is 1 micrometer. Plugging into the equation that we saw earlier, where the change in impedance is equal to 2 rho r cubed over pi r channel to the fourth, you're going to find that delta Z, plugging all that in there, is going to be 6.3 ohms. Now that's pretty shocking, and again, that's why I tell you not to really round off too much, because we're talking about a 6.3 ohm change on top of a 70.74 kilo ohm resistance. So that's 4 orders of magnitude difference, right? So this is a 3 orders of magnitude is 1,000, but then you have it's 70,000. So this is 4 orders of magnitude larger. So that's quite a small change, and this just goes back to the fact that this is why you should use a bridge to measure these impedance changes, because this is such a large resistance, and to measure that small change, and to measure it in terms of a voltage, you want to use a bridge so you can zero out your base impedance in that case. So if we move to a basophil, then let's say, okay, well, that's going to have a diameter of 10 micrometers, like I mentioned, so a radius of 5 micrometers. Plugging it in, you're going to get delta Z is 785 ohms. That is, 100 times, over 100 times more than what you got out when you had a 1 micrometer radius. So a 5 times change in radius will yield 100 times or more. Well, obviously it's to the cube power change in resistance. So that's quite a bit. And so yes, a few micrometers does make a difference in terms of the kind of impedance changes you're gonna measure when you're doing this. An iteration of this problem that I encourage you guys to work on is if I ask you to design a bridge circuit that would measure these differences, and then for your bridge design, tell me what kind of voltage changes will you get. And if you want to go even more sophisticated, if you wanted to, for your bridge design, if I asked you what is the sensitivity to resistance changes, that would also be a pretty good problem to try to work out for yourself. Okay. So that ends the Coulter counting portion of this lecture. What I did want to do is I did want to go over some introductory information regarding ECG and EEGs. So let's kind of get to that. So please work on the problems, but let's move on to the next set of slides. Alright, so I haven't posted these on Canvas just yet, so I'll post them as I post this video. But let's talk about ECGs, EEGs, and EMGs. But before I get to that, which we'll get to on Tuesday, I did want to go over some origins of biomedical signals, and then we'll kind of cap the lecture off at that point. Okay, so before talking about ECGs, you have to understand the origins of voltage production in your body. I think we all take for granted that when if you've ever gotten an ECG, where that voltage actually originates, what is it actually telling you. Let's get to the heart of where that comes from. So for this part of the lecture, we're only going to be working on an individual cell basis. So we'll talk about the voltage that's produced across the membrane of a cell. But you have to always keep in mind that we have trillions of cells in our body. And not all of them are going to be electrically active, but the ones that are, there's still millions of them present. And when they work in unison, you can actually get quite a large signal, quite a large electrical signal that kind of emanates from their location, and that you can measure on the surface of your skin or any location in your body, if you are strategic about it. So let's talk about this thing called the resting membrane potential. And a word of warning here, this is going to be some physiology, but I promise that it's going to give you some context as to why, like where ECGs and EMGs and EEGs come from. Okay, so let's talk about bioelectricity. That's the naturally occurring phenomena arising from the flow of ionic current in the body. Because you have these ionic currents in your body, you're going to have then voltage changes that are associated with those phenomena. A little bit about ionic conduction. So it involves the movement of ions. Like I mentioned before, we can model the human body as basically an electrolytic solution that has various concentrations of ions like potassium, sodium, calcium, chlorine, etc. Voltage differences or potential differences occur when there are different concentrations of different ions at different points. And you're going to see that in the next couple of slides. You're able to detect relatively large voltages and like on the order of microvolts and millivolts on the surface of your skin, because some of these cells are very electrically active, which means that they have a propensity to allow ionic flow to go into and out of their membranes. And because of that, and because a lot of these will work in synchrony, you'll be able to detect some of those voltages at a given part of the body. But you do have to be strategic about where you place some of the measurement instruments for these. Okay, I want to give you an idea of some of these pictures here. So these ionic currents can occur in the brain, where there's a lot of neurons. We'll see that there's trillions and trillions of neurons in your brain, and so we'll get to that. And those potentials that you can measure that are associated with the brain activity are called electroencephalograms. So they're abbreviated as EEG. On the right there, you're going to see a heart. Your heart muscles are also electrically active. With that, again, that means that they allow ionic currents to flow into and out of the cells. And in this case, they're going to produce voltages on the surface of your skin near the chest or the thorax, and that's called an electrocardiogram. So those are usually have abbreviated as ECG, or sometimes you'll have it abbreviated as EKG. The same thing. On the bottom here, this is actually a really old image of one of the first experiments done on frogs. But we're also going to learn about muscles. Muscles are also electrically active, and the potentials that you'll measure for those are called electromyograms, and so that's abbreviated as EMGs. Okay, so let's talk about the origins of a resting cell potential. All right, so before I move on, I just kind of want to give some definitions. So there are two types of ions. There are those that are net positively charged and those that are negatively charged. The positively charged ones are called cations, and the negatively charged ones are called anions. And just as we move forward, just keep in mind, that we're going to talk about conservation of electrical charge. So there's no net amount of charge produced. So you're going to be electrically neutral, and that opposite charges attract. So let's take a scenario down here where we have a cell, and you have the volume that's inside the cell. Remember that that's called the intracellular fluid, and then you have the volume of fluid outside the cell, which is called the extracellular fluid. And in this scenario, the cell is going to have a membrane. Whoops, let me go back. It's going to have a membrane, and for now, in this case, the membrane is not permeable to any ions. What that means is no ions can cross the boundary across the cell. Alright, so in this scenario, it's pretty simple, right? On the inside, you have equal number of positive charges as you do negative charges. You can prove that to yourself, unless counting is hard for you. You can also do the same thing for the outside, where you can count the number of ions inside and outside the cell. So a couple of things here. In this case, because we're electrically neutral inside and we're electrically neutral outside, there are no forces, no electrical forces that are driving or wanting to drive positive or negative charges into or out of this cell. So those are zero. It also turns out that we're also chemically neutral, because, and this is not an obvious thing, because you're probably counting the number and you're like, wait a minute, there are more negative of these if they're all the same, anions, and there's less that are inside. Remember that we're talking about concentrations. So for the number of particles per unit volume, it turns out in this case, are going to be the same as those that are on the outside. That's not apparent, but the concentrations are different, and because you have a smaller volume in the cell, you're obviously going to have smaller number of anions. But in this case, we're saying that the chemical concentrations on the inside and the outside of the cell for both of these ions are going to be equal. So in that sense, there's also no chemical forces that are pushing these chemicals into or out of the cell. Okay, so now let's take a scenario where we have, let's say, a protein that's sitting on the membrane of this cell, and say that protein only lets out one positive charge. Okay, and it just does that, and then that's it. So that creates a scenario that's a little more complicated. So obviously, when you push the positive ion out, you're making the inside more negative, and it's more negative because now you have 4 negative ions inside the cell, and you only have 3 positive ions inside the cell. So you're going to have a negatively charged environment on the inside of the cell. But you've also kind of created a more positive charge on the outside of the cell as well. So you've gained a positive ion on the outside. So what that's going to effectively do when you have a difference in potential across a insulating membrane, that's going to produce a voltage or an electrical gradient or electrical force that's wanting to push the positive charge back inside. Okay? The other thing you've done is now you've also messed with the chemical concentrations of the inside of the cell and outside of the cell. So now you've effectively decreased the concentration of the positive ion inside the cell, and you've increased the concentration on the outside. What that does is that also creates another force, and it's a chemical force that's wanting to push again back the positive charge back inside for chemical reasons, to keep the concentrations the same. So I just want you to keep those two ideas in mind, that you're going to have two forces that may be going in the same direction or in opposite directions, but at the end of the day, you're going to have two forces that are driving the movement of these ions into and out of the cell. Okay, so with that, in the previous scenario, it turns out that if you were to put a generic cell in a saline bath, which is an electrolyte, and you were to get a really small electrode and puncture the cell membrane to get access to the inside of the cell, and if you have a reference electrode on the outside of the cell, so the extracellular fluid, it turns out that you're actually going to measure a voltage across those two electrodes, and that voltage on average is going to be negative 70 millivolts. And that's what we're going to call as the resting membrane potential of the cell. So here's another example on the right here. So say you're given like a neuron that's going to be a electrically active cell, that is responsible for the transmission of signals in your nervous system. And again, if you were to open this little cell up and you were to put a electrode inside the actual cell and outside the cell, you would measure about a negative 70 millivolt voltage difference. And we'll see the origin of that negative 70 millivolts in the next couple of slides. But you do have a voltage present, and so that's kind of the take-home message of this slide here, is that at resting, when there's no signals that are moving through these cells here, they have a inherent voltage that exists across the membranes of these cells. Okay, so now how exactly do you get, let's take a scenario where, as say you're watching this video and I'm, completely boring you to death. And in your mind, you've decided, I'm going to turn off this lecture. And to do that, I'm going to get the mouse, and I'm going to just pause this YouTube video, and I'm going to go get a sandwich. So if that decision is being made in your brain, and there's some signal that's going to your arm to click on that mouse to pause this video, right? I'm assuming you're going to do that. So how does that signal, and what is that signal, right? And how does it get to your muscles, and what does it have to where does it have to travel? How fast does it have to travel? What kind of processes will enable you to do that and make that decision and make that action? So we're gonna get to that soon. I know I keep teasing you, but now let's get into a more complicated scenario and talking about, okay, well, first of all, how do you get the negative 70? Like, why isn't it negative 90? Why isn't it positive 70? And that has to do with the next slide here. So let's take again another artificial cell, and let's say that in the first case, this cell is initially not permeable to all ions. And in this case, we have a simplistic kind of scenario where we only have 4 ions. We have a potassium, which are the little diamonds. We have Pr minus, which I don't really know what that stands for, but it's going to be a generic anion that's inside the cell. And then on the outside, you're going to have basically salt. You have sodium, Na+, and chlorine, Cl-. So now we're putting actual names to these ions. So let's talk about the kind of forces that are driving them. When the cell is initially impermeable to these ions, you're going to have a couple of forces that are pushing them in and out. So let's talk about the electrical forces. So first, let's count the number of negative ions. 1, 2, 3, 4. Positive ions. 1, 2, 3, 4. So you're electrically neutral on the inside. Same thing on the outside, right? You have 4 sodiums, you have 4 chlorines. You're electrically neutral on the outside. But you have no potassiums on the outside. You have no sodiums on the inside. You have no Pr minuses on the outside. You have no chlorines on the inside. So each of these individual ions are going to have a chemical gradient that are pointing them to equilibrate the concentrations inside and outside of the cell. So for instance, potassium, you're going to have a chemical gradient that wants to push potassium to the outside of the cell. You're going to have a chemical gradient for chlorine that's going to want to push chlorine to the inside, and etc. Okay, so now let's let all hell break loose, and let's let the membrane be permeable to a specific ion. So let's say you have a channel on your membrane that allows potassium to leak out. Because I mentioned to you before, because you have potassium on the inside and there's a depletion, or there's literally no potassium on the outside, there's going to be a chemical gradient pushing potassium to the outside. So when you allow this leakage, you're going to then naturally have potassium leaving the inside of the cell. So that's going to cause kind of a chain reaction of a couple of things. So let's take it one by one. If you have potassium leaving the cell, you now have induced an electrical gradient or electrical force, right? You've now made the inside of the cell more negative than the outside. And so you're now going to have an electrical force that's going to want to push potassium back to basically make the inside of the cell neutral again. So that's going to be opposing the the chemical gradient that wants to push potassium out, right? And so there are going to be these two opposing forces, and at the end of the day, none of them is going to win. At least for potassium, right? You're going to have potassium going out, but you also want it to go back in because you want electrically neutral. And at some point, there's going to be a compromise where even though we don't have the same concentration of potassium on the inside as the outside, you're also going to have something that's a little closer to electrically neutral, but not quite electrically neutral. So there's going to be some point where the concentration gradient is going to equal the electrical gradient for potassium. And that at that point, there's going to be a voltage difference across the cell membrane that is solely contributed by just the potassium. So we're still ignoring like PR minus, Na plus, Cl minus. So we're going to call that the equilibrium potential of potassium, right? So that's going to be a voltage that is associated with just potassium. And again, what that means is that doesn't mean that once the concentration gradient is equal to the electrical gradient, you're going to have equal concentrations of potassium on both sides of the cell, and you're going to have neutral electrical properties on the inside and the outside. It just means that the forces are the electrical and the chemical forces are counteracting each other in such a way that there's a compromise, and they're equal to each other. So there's no longer a flow of potassium going into or out of the cell. So, like in this specific example, it hit equilibrium when potassium there's 3 of them inside and there's 1 on the outside, and that's it. So that voltage for potassium can be calculated by using this equation. So E is just the potential or the voltage contributed by potassium, so K, and it's equal to 61 over Z, Z being not impedance, but Z being the valence of potassium, so it's plus 1, times the log of the concentration of that ion on the outside over the concentration of that ion on the inside. And I'll give you some numbers in the next slide, but you can also do this same scenario, and I encourage you all to do it for PR minus, do it for Na plus, and Cl minus. And each of those individual ions are going to contribute an equilibrium potential to the cell membrane. And this is where you can have that drum roll, please, because that's how you actually get the membrane voltage. It's a contribution of all of the ions and all of their equilibrium potentials to that cell. So here's the table that gives you some ideas of some of the concentration differences of a generic cell. So let's say like for potassium, on average you're going to get that potassium has about 5 millimolar on the outside of the cell and 150 millimolar on the inside of the cell. So obviously there's a lot of potassium within cells and not a lot on the outside. So you can see where the chemical gradient is pointing. It's pointing to try to effectively push potassium out. So there's going to be an electrical force that goes in the opposite direction. And once those equilibrate, for potassium, its equilibrium potential is negative 90 millivolts. So what that really means is if you were to apply negative 90 millivolts across the cell membrane, that you would ensure that you don't have any potassium that's going to leave the cell. And you can do the same kind of thing for sodium, chlorine, and calcium. And again, just plug in these numbers in the previous equation here, and you should get the same values on the right side of this table. Okay, so because you have lots of ions, they all contribute some amount of equilibrium potential to your cell that effectively is will result in having a cell resting membrane potential, and this is the equation you're going to use. And let me define some things. So these P's that you see here, PK, PNA, PCl, PK, etc., those all just stand for the permeability of potassium, sodium, or chlorine, or any ion for that matter that's of interest. Those are going to be just numbers that will be given to you. and they'll have a wide range of values from like zero point 0.1 to thousands, depending on how permeable the cell membrane is to that specific um, ion. And what I'll say is, right now we're talking about a generic cell. So, like for instance, a cardiac cell will have a very specific set of ions that are contributing, and it will definitely have a different membrane resting potential. So, if you wanted to calculate the resting membrane potential, so that goes back to the previous slide. So this negative 70 millivolts, where does it come from? That's where you get, that's where you use this equation right here. So it's basically 61 times log base of this giant ratio here. And on the numerator, you're going to have the permeabilities multiplying the concentrations of those ions on the outside of the cell, unless you're talking about the negative ions, over the denominator, which are the permeabilities times the concentrations on the inside of the cell, unless you're talking about the negative ions. So just make sure you follow this rule here to basically calculate what the resting membrane voltage is for a given cell if you're given these different concentrations for the cell. Before I leave this slide, it's going to come up later. It's, instead of just memorizing equations, which certainly a lot of you will do, I want you to kind of like play with it in your head a little bit. What will change the membrane voltage of a cell, right? So think about it that way. Don't just think about it, oh, okay, if I want to calculate, just plug and chug, right? There are two things exactly that will change the cell's membrane voltage. And this actually happens in real life. So one way to do it is to change the extracellular and the intracellular concentrations of the cell. So you can do that, by doing it in the lab, or your body does it as well when certain processes happen. So that's one way. The other way is that you can actually change the permeabilities in time. And again, your body actually does this. So certain cells will change their permeabilities in time. And so again, for this equation here, permeabilities of ions and the concentrations of ions inside and outside the cell will dictate the membrane voltage and how it changes. And that's an important concept because if you ever go into this, in the biomedical field, and if you ever go into, like neuroengineering, you will have to basically, study this and be aware of how action potentials, which we'll get to later, are produced, and they're produced as a function of these changes. And if you wanted to model this, you can model that using whatever engineering skills you have. Okay, so I'm gonna just briefly introduce the action potential and really just preface it with definitions, and then we'll get to the actual meat of the lecture in class. So before I get to what an action potential is, I want to just define some things here. Let's say you have your resting membrane voltage across your cell, and again it's negative 70 for our generic cell. That's just the voltage difference from 0. The process of becoming less negative is called depolarization. So, and in that case, you're decreasing the membrane voltage, you're making it less negative. The process of going back to the resting membrane potential is called repolarization. And again, in that case, you're going back to the original resting membrane, VM. The process of going more negative is called hyperpolarization. And then, so that's the definition. And so depolarization would be then going back to resting from hyperpolarization. Okay, so let's talk a little bit about how we get voltage spikes that essentially carry information. And I think this is where I stopped the lecture. Yes, when I first recorded this. I certainly went faster than the first time. I don't know what I was mumbling about, I guess, the first time around. But before we get to action potentials, I want you to kind of realize 3 concepts here. Because these are gonna generate the signals that are propagating very quickly from your brain to any other motor neurons that are, basically in your arms or legs or your eyes, etc. So the first key concept is that ionic movement, so the movement of ions like potassium, sodium, and chlorine, and the changes in ion permeability across the cell will generate electrical signals. And the reason why that should make sense to you at this point now is because I just mentioned it before, right? That a cell's membrane voltage is a function of the concentration of ions inside and outside the cell, and also the permeability of those ions of that cell. So that's the first thing. The other concept is that you are going to have these molecules and proteins that are sitting on the membrane of cells, which are called ion channels, and they can be what's called gated, so they can be opened and closed by different forces or different reactions, and they control the permeability of ions. And that has repercussions because I just mentioned to you that the permeability of ions also dictates the voltage of cells across their membrane. So here are just three simple examples, but there are ion channels that are voltage gated, which means that when you have a change in the voltage across the membrane of a cell, that they will open or close depending on that voltage. Now, why is that important? You're probably wondering, wait a minute, what comes first, chicken or the egg? Does the voltage change first, or does the ion channel open, or what comes first? Well, it turns out that this is actually the basis for how signals travel. At some point down the line here, so say this is a cell and it extends from to the left and to the right. At some point, something's going to happen where you have an inflow of ionic current into or out of the cell, which will cause a voltage change over here. That can be felt by these voltage gated channels, and they will then open and close. And if there are more of these voltage gated channels along the length of this thing, that kind of creates like a domino effect of ionic flow now propagating along a distance, the distance that you have these voltage gated channels. So that's one kind. You can also have ligand gated. That's the fancy way of saying that sometimes chemicals will latch on to some of these ion channels, these proteins, and then it'll change shape and open and close depending on what's attached. One specific kind of ion channel that exists on your tongue are called capsaicin ion channels. So they have capsaicin receptors. So what's capsaicin? Capsaicin is the chemical that you basically eat when you eat chilies or anything kind of spicy tasting. That molecule specifically attaches to these capsaicin receptors, which will open these channels and allow the inflow of ionic current into the cell, and that'll generate basically a signal that then gets propagated to your brain to tell you, hey, I'm eating a habanero and I'm enjoying this, or I'm not enjoying this, this is burning my tongue. You also have tension gated, which effectively are just like pressure. So these you have on your hand, for instance, so you can feel like different pressures. You have all sorts of different kinds. What's not mentioned here is like temperature sensitive ones, so that's how you can tell that you're burning your hand when you're placing it on like a hot stove or something. So yeah, so that's the second key concept. The last one is that there are two types of membrane potential changes, and there are called graded potentials and action potentials. Graded are just another way of saying that they are voltage changes that don't meet a certain threshold to keep on moving. So you're gonna find that these are like voltages that will decay over a distance and not really result in anything. And then there are action potentials, which are voltage changes that meet a certain threshold that then cause an all or nothing reaction that will then get that result basically in a signal being propagated along the length of a neuron. Okay, so I'll stop it there because I think that's quite a bit of information, and then next time we'll cover specifically graded and action potentials, and then talk about some instrumentation to how this all relates to like ECGs and EMGs and EEGs, and what kind of instruments you would need to measure these kind of signals. Alright, so I'll stop it there, and thank you for listening, and take care.